Um, Good evening, everyone. My name is Harini. I'm a PhD student from Interdisciplinary Center for Water Research at Indian Institute of Science. Currently, I'm doing teaching assistant duty for NPTEL lecture offered by Professor Rajiv Kumar Bhattacharya from IIT Guwahati for the course Optimization Techniques for Civil Engineering. Uh, so, let's First, what we will do is when I was explaining in last class how we will solve uh, op- optimization problem for a single or multiple variable problem using Newton's method. There was small calculation error, I was confused with 2 cross 1 into 2 by 2 matrix multiplication, right? So I'll just explain that part little bit and then we will start our lecture, okay? So in last class we discussed about um, multiple variable optimization. So in that one of the method is using Newton's method. So the problem was f of x comma y equal to x minus y plus 2x square plus 2xy plus y square. And the initial x1 is, we will start at 0 comma 0 transpose. Okay. So what was happening was when we are finding the roots, n plus 1 equal to xn minus del of f of capital X. This is capital X, okay? X by Hessian matrix of X. That's how you do, right, for this? So first, you need to calculate del of X, that is dou F by dou X by, and the second row is dou X by dou Y. So that's 1 plus 4x plus 2y minus 1 plus 2x plus 2y at of x at 0 comma 0 will be, just substitute 0 comma 0, it will be 1 minus 1. Okay, then we are calculating dou square of x, that is dou square f by dou x square, dou square f by dou x dou y, then dou square f by dou x dou y, then dou square f by dou y square. Okay, so that will be equal to 4, then 2, 2 and 2, right? So this is how we got. So in this case, what we can do is xn plus 1 is equal to xn minus first differentiation of f of x plus second divided by second differentiation of f of x. So this, if we take xn x1 y1, because initially it is 0 x naught y naught, that is 0 comma 0, minus this term will be 1 minus 1 divided by, I'm just representing like this. Okay. Okay, so when we do it like this, if you bring this to the right hand side, it will be directly x1 y1. Okay, and this differentiation will become multiplication, right? So it will be here, or you are just multiplying minus 1 1. So you can also take like this 4x1 plus 2y1, 2x1 plus 2y1. Matrix multiplication we are doing 2 by 2 and 2 cross 1. Okay. So it will result in 2 cross 1 matrix. It's equal to minus 1 and 1. So just by solving these equations where 4x1 plus 2y1 equal to minus 1 and 2x1 plus 2y1 equal to 1, then just subtract these two equations, then 2x1 equal to minus 2. x1 equal to minus 1. Similarly, substitute this in the first or second equation. So 4 into minus 1 plus 2y1 equal to minus 1. So 2y1 equal to 3, y1 equal to 3 by 2. So therefore, the minima we are trying to find. So minima exists at minus 1 comma 3 by 2. Just solving this, because we already did this, but I just wanted to show here we got a little confused, right? So that's why I'm showing it here. So that's one problem, and I have one more problem on Newton's method. Then I'll give brief definition of what is convex function, and then we will start today's lecture on a quadratic approximation of optimization. Okay. So I'll be giving problems. If you have any doubts related to that, you can ask me. So next, second question is, we have equation x minus 5 ln of x plus 3 equal to 0. Solve it using Newton's method, the roots of the equation. Okay. Um, so shall I wait for 1 minute? You can tell me the answer. So it's a single variable problem. Problem in X. First, can you give me what is the equation of xn plus 1? Yeah, I'll start the solution. You can tell me the answer if you are solving it side by side. Okay. So xn plus 1 to find the roots. We know from Newton's method it's f of x by f dash of x. Okay. So xn plus 1 equal to x n minus f of x is x minus 5 ln of x plus 3. F dash of x is, if we differentiate this with this equation with this function with respect to f of x, f dash of x, it is 1 minus 5 by x. Okay. So xn plus 1 equal to, I'll just keep it as x for now. Okay. X into x minus 5 ln of x plus 3 divided by x minus 5. So it is equal to x into x minus 5 minus x into x minus 5 ln of x plus 3. So when we solve this, x square minus 5x minus x square plus 5x ln of x plus 3x x minus 5. So that's equal to 5x ln of x minus 2x by x minus 5. So it's equal to, I'm taking x out, 5 ln of x minus 2 by x minus 5. So this is x plus 1. So suppose we have initial assumption x1 equal to 1, then x2 will be 1 into 5 ln of 1 minus 2 by 1 minus 5. So x2 equal to, ln 1 is 0. So 0 minus 2 by minus 4. So that's equal to, it's correct, right? Whatever I did. So it's 1 by 2. So that's the answer we have. Okay. Also in the assignment, when I checked in this week's assignment, I have seen few problems from next week assignment, like when we have inequality constraints. So I have one problem. I'll just explain the steps how to do solve that problem. Okay. Because in next week's lecture, we will be discussing how we will solve. The methods are mentioned in the next week lecture. Next, we will look into what is convex and con Yeah, in week 5 assignment, yeah, that's discussed next week actually. Yeah, the okay. Okay. Okay, then it's fine. Okay. Because when I checked, it's I mean, it's not actually the concept is not discussed in this week, so I thought maybe yeah, yeah, yes, yes. That's yeah. Okay. So what is convex function? Suppose if we have a function like this and we are joining, we have 2 points on it and we are joining it, then this line will always lie above any point on the convex function. Okay. So from in between A to B, if you see the convex function, this function is lying below the line joining the points A comma B. That's how we define convex function. We have a equation for that, f of lambda x2 plus 1 minus lambda x1. I'm just giving a recap, so I'm not discussing how to derive and all. So did it. So is less than or equal to f of x2 plus 1 minus lambda of f of x1. Okay. Yeah. So this represents the point on convex function between x and y, x1 comma x2, and this represents the line joining the points x1 and x2. So where this is called convex function. This is the definition. Less than or equal to case is convex function. But in the case of strictly convex, what will happen is the function f of x2 plus lambda x2 plus 1 minus lambda x1 is less than lambda f of x2 plus 1 minus lambda f of x1. Okay. Here we don't have equality sign, only it is less than sign. So then it is called strictly convex. So in the case of concave, also if you see in convex function, we have the function will have a minimum. Okay. And if we know that it is convex function in the range a to b or x1, x2, then whatever minima we have, that will be equal to global minima. Okay. If it is convex in between a particular range, okay, in particular values of x and y, x-axis a to b, like here I have shown. So the minima that exist will be global minima in that particular range. Okay. In the case of convex function, if you see, the line joining the 2 points will always lie below the points on the concave function. Okay. So if you see, if this is x and y, the values on the concave function are always higher than the values that are lying on the line joining between a and b or x1 comma x2. So that condition is written as f of lambda x2 plus 1 minus lambda x1 is greater than or equal to lambda f of x2 plus 1 minus lambda f of x1. So the function values are always greater than or equal to the value on the line joining x1 and x2. So in the case of strictly concave, we have f of lambda x2 plus 1 minus lambda x1 is greater than lambda f of x2 plus 1 minus lambda f of x1. Okay. Here we don't have equality sign, only non greater than sign in the case of strictly concave. Okay. And also, sir discussed a few theorems related to it. One is like I have explained, if we have local minima for a convex function, then it leads to global minimum. It is equal to, so in the same case, if we have local maxima in case of concave function, then it will be a global maxima. Be sure that the function is concave or convex. If we don't know what kind of function it is and we are seeing a local minima, it can be a local minima or global minima. Okay, accordingly, you have to answer. Then also we know that for a concave function, the Hessian matrix is positive semi-definite matrix. And also there is one more theorem. F of x is convex function between x1 and x2. Then we have f of x2 is greater than or equal to f of x1 plus first differentiation of function f of x1 into x2 minus x1. This is one theorem. Okay. So you can find the proof of this in the first lectures. Next, I'll just give one problem related to this convex and concave. Mhm. Yes, strictly convex. Yeah, concave function. Yeah. So, just remember it like this. If you remember, if when we have single variable function, okay, and where we will have maxima or minimum when f dash of x is 0, right? And based on f double dash of x value, we will know whether it's a minima or maxima. If it is negative, then we have maxima. If it is positive, then we have minima, right? Similarly, for multiple variable also, we know f dash of x, that is all the partial differentiations, okay, with respect to x will be equal to 0, where there is optimum, minima or maxima. And similarly for this case, what we have to do? We have to do double differentiation also. In double differentiation, to understand whether we have maxima or minima, so if it has positive definite, if the Hessian matrix is positive definite, sorry, like here, if it is positive sign and here it is positive sign, then we have minima. When minima exists, when it is convex function. And if it is a negative, yes, yes, yes. In the case of negative definite, we have maxima, and then in that case, concave. And yeah, like you said, when strictly convex means eigenvalues are all positive. Okay, are all positive. it won't be equal to 0. Okay, any of the value. In the case of strictly concave, we have eigenvalues are all negative. And they won't, any one, one or more than one, they won't be equal to 0. Okay, this is clear. Just like from single variable problem, you can get an understanding of multivariable also. But in this case, we use eigenvalues because we cannot get uh, constant value for a matrix, right? So we look into eigenvalues to get an idea of it. Yeah. Hmm. Okay. 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 No, when you have a true and false, if the when you have a true and false question, if it is absolutely correct, then only you have to say it's true. If there are conditions that exist that makes it false, then you cannot. Yeah. Okay. Um, okay. I need to look into that questions. Because okay. Okay. Yeah. Um, so okay, there is one question. F of x1 comma x2 is equal to x1 square minus x2 square plus minus x3 square plus x1 x2 plus x1 x3 plus 2x1 minus 5x3 plus 2, and whether this function is convex function or not. That's the question. Can anyone tell me how can you put x2 and x3 0? But how univariate method tells you whether it's a convex or concave? How can you say that? No, it's a three-dimensional function. So if it is convex in one direction, you cannot say that it's convex in all the directions, right? I mean, if you, I mean, it can be in one particular direction, but doesn't mean the entire function has to be convex in all the directions because it's a three-dimensional question. So for this case, like I have discussed, right, you can use uh, Hessian matrix to understand whether it's a convex or concave function. So basically, you have to do double differentiation of the function. Okay, that will be dou square f by dou x1 square. Okay, one second. Oh, I think I have given the wrong problem. One second. It will be a complex thing, yeah. Yeah, but you cannot do that. You cannot put one thing zero and then do, because that can't tell you whether it's convex in all the directions. Because when I actually this I prepared in last week, so I did all this and then now I kind of forgot. So can I get back to you guys about this problem next week, and also your questions related to last week 4 assignment problem? Okay. Yeah. So they said it's in an optimization problem, the local minima is unique, right? Then it is global minima. But do you know whether the function is concave or convex? Or it's not any, I mean, minima is there, but do you know it's a convex function in the statement? Yeah. So suppose you have like this, okay? This can be local minima and it can be unique, right? So it can't be global minima. This will be our global minima, right? Yeah. So, like, if they have mentioned that it's a convex function in this range, and then you have, yes, because they didn't mention that there can be other, because other minimas also that exist, which can be one of the global minima. So that's why when you are sure, when you don't have any other alternatives to contradict it, then you can go. I mean, it's a true statement or false statement. Okay. So, okay. Then week four's assignment problems, you are asking about concave and convex, and then, okay, I'll discuss this in next week. So now what we will do is we'll look into uh, quadratic optimization. Okay, so you guys know how we will define a quadratic equation. If the higher order power of it is 2, then it is a quadratic equation. But not all the, I mean, sorry, function. So if the function is not quadratic, then how can you solve it? Um, because, like, if I have single variable f of x square plus 2x minus 3, then you guys know how to get minima or maxima for this function. You'll just do f dash of x, f double dash of x. You find where f dash of x is 0 and what is the sign of f double dash of x at that point. Then you will know whether it's a minima or maxima. But if you have a function like f of x equal to e power x plus 5x square plus 4x, then is it a quadratic equation function? It's not, because we have e power x. Okay, even though here the power is 2, but we have a e power x, so it is not a quadratic equation. Similarly, if you have any trigonometric equations, then also it's not a quadratic function. So in this case, what you can do is we will do quadratic approximation. So in quadratic approximation, what will happen is, if we have a function f of x equal to e power x plus 5x square plus 4x, then we will approximate this in the form of ax square plus bx plus c. This is quadratic, right? And how we will do is, we have Taylor series expansion is f of x naught plus f dash of x naught into x1 minus x naught plus 1 by 2 f double dash of x naught into x1 minus x naught whole square. So we can extend for higher order differentiation, but for now we are restricting to only second order differentiation, okay, in this case. So if you see, suppose we have a function f of x equal to uh, 2x power 4 minus x cube plus 5x square minus 12x plus 1. This is what sir has discussed in this in his lectures as well. So how he is doing that, we can also do like directly f dash of x equal to 0 and find the solution for this. But because this is a very simple polynomial function, like higher order function, so we can do that also. But for this, if we try to do quadratic approximation method, then what we can do is f of x naught plus f dash of x naught into x1 minus x naught plus 1 by 2 f double dash of x naught into x1 minus x naught whole square. In the case, let's start with x naught equal to 0. Then f of x naught will be 1. I'm just substituting f of 0 value in this function. F dash of x will be 8x cube minus 3x square plus 10x minus 12, and f dash of 0 value is minus 12. And next we need to also find f double dash of x, that is 24x square minus 6x plus 10, and f double dash of 0 is 10. So if you see, I mean, sir has done the computation very quickly. And he got the next equation. So I just want to show you how he got the first iteration equation. Then it will be repeated multiple iteration till you have a f dash of where we'll find x value, which will make f dash of function. This is the function 0 at that particular point. Okay, so f of x1 is equal to f of x naught is 1, f dash of x naught is minus 12 into x1 minus 0 plus 1 by 2 into f double dash of x naught is 10 into x1 minus 0 whole square. Okay, so that is 1 minus 12x1 plus 5x1 square. So this is the quadratic approximation of the function when x naught is equal to 0. Okay, so this case what we will try to do is f dash of x1, we try to make it 0. Then we will find x1 star, the optimum value of the, I mean, optimum where the x1 star value where the function f of x1 will be optimum. Okay, but this doesn't have to make our main equation f of x also optimum at that particular point. Okay, so that's why we go for other iterations. Is this clear? Is this step how we are doing? Okay, yeah, so we have to do it till our main function. We find a x value where this function f dash of x will be equal to 0. And based on f double dash of x sign, we know whether that value is a minima or maxima. Okay. Similarly, in the case of, this is for single variable. In the case of multiple variable, what we have to do is f of x1 is equal to f of x naught. I'm just doing Taylor series expansion in multiple variable framework. X minus x naught into del of f of x naught plus 1 by 2 into x minus x naught del square f of x naught into x minus x naught whole transpose. This is how the multiple variable problem looks like. Okay. Uh, Similarly, we have to do multiple iterations till we know our main function f of x, okay, is having a optimum value at that particular point. In that case also we need to see del of f of x star should be equal to 0. Okay, then we will know the optimum. So solve problems related to this topic. We have a function f of x equal to x power 4 plus 3x cube plus 2x square plus 5x plus 7. Okay. At x not equal to 0, give me Taylor series approximation of this function. This is single variable. Okay. Remember, whenever I'm writing small x, then it's a single variable. If I'm writing capital X, then I'll show you. And also I'll give you if multiple variables are there, x1, y1. I'll show. I'll just go one by one, right? Like I'll give you problems. Okay. So can you guys tell me what is the Taylor series approximation or quadratic approximation for this function at x naught equal to 0? Okay. So for that, first what we will do, f of x1 is equal to f of x naught plus f dash of x naught into x1 minus x naught plus f double dash 1 by 2 times of f double dash of x naught into x1 minus x naught whole square. So f of 0 is 7, f dash of x is 4x cubed plus 9x square, 7 plus 5x1 plus, yeah, 2x1 square. Yeah, that's correct. Yeah. So 4x plus 5, this is f dash of 0 is 5, then f double dash of x is 12x square plus 18x plus 4, then f double dash of 0 is 4. Therefore, the function quadratic approximation will be f of x1 equal to 7 plus, I'm just substituting these values which we got from here. Okay, 7 plus 5 into x1 minus 0 plus 1 by 2 into 4 into x1 minus 0 whole square. So it's 7 plus 5x1 plus 2x1 square. This is the problem. Okay. So in this case, we first find where f1 dash of x is equal to 0. Okay. Then we will try to see whether at that particular point we got x star value, whether at that particular x star we have a optima or not. When the optimum will exist, f dash of x star should be equal to 0. Okay, not f dash of x1. Okay. So if not, we will repeat the iteration taking this as our initial point, x naught, in the next step. And then do the similar computation. Okay, next question is, we need to get quadratic approximation. If they say Taylor series approximation or quadratic approximation, then you'll be doing the same problem. F of x for a single variable e power 2x plus 3x plus 4 at x equal to 0. I'll just wait for 1 minute and then I'll start. You can tell me the answer. I'll just give solution again for others. So, how we will do approximation? F of x1 equal to f of x naught, f dash of x naught into x1 minus x naught plus f double dash of x naught into x1 minus x naught whole square by 2. So, f of 0 value is e power 0 is 1. So, 1 plus 4, 5. F dash of x is 2 e power 2x plus 3. So f dash of 0 is 2 plus 3, 5. F double dash of x is 4 e power 2x. So f double dash of 0 is 4. So just by substituting this, f of x1 is 5 plus 5 into x1 minus 0 plus 4 into x1 minus 0 whole square by 2. Therefore, it is 5 plus 5x1 plus 2x1 squared. This is our first approximation that we get when x not equal to 0. Okay, is this correct? Okay. So next is, we have a function f of x comma y equal to sin x cos y. Can you get quadratic approximation at x comma y, x naught comma y naught equal to pi by 2 comma 0. So this is a multiple variable problem, x comma y, and the function is sin x cos y. So we need quadratic approximation at x naught comma y naught equal to pi by 2 comma 0. So I'll wait for 1 minute. Any answers? Okay. So first, if you remember how we are doing x1 comma y1, f of x1 comma y1 equal to f of x0 comma y0 plus del of f of x0 comma y0 into x minus x0 plus 1 by 2 into x minus x0 del square of f of x0 comma y0 into x minus x0 whole transpose. Right? So for this, what we are trying to do here is, first let's find f of x0 comma y0. That is sine pi by 2 cos 0. So it's 1. Okay. Then what do we have? Then we have to find del of f of x0 comma y0. Okay, first let's calculate del of x0 comma y0, x comma y. So that's equal to mm, dou f by dou x and dou f by dou y. Okay. So that's first we have to differentiate this with partial differentiate with respect to x. So derivative of sine x is cos x, cos x, cos y. Then we have to differentiate, partial differentiate this equation sin x cos y with respect to y. So differentiation of cos y is minus sin y. So it's minus sin x sin y. Okay, and then we have to find pi by 2 comma 0. So cos pi by 2 is 0, right? So first one will be 0. And then if you see here, y is 0. So sine y, sine of 0 is 0. So we have 0. So first partial derivation is 0 at pi by 2 comma 0. Okay. Then from here we can have a slight idea that there might be optimum at that point also, because first derivative is equal to 0. And just for this particular case it is happening, but it doesn't have to happen in all the cases that we our first partial differentiation at the given points of x naught comma y naught will be equal to 0 comma 0. Then we have to find second derivative, the function f. So in that case it is dou square f by dou x square, dou square f by dou x dou y, then dou square f by dou x dou y, dou square f by dou y square. So in this case, what is happening is, what is the second derivative of this particular function? We have to derive cos x with respect to x. Okay, so differentiation of cos x is minus sin x. So it's minus sin x cos y. Then this one we are partially differentiating with respect to y to get the second term. So differentiation of y with of cos y is minus sin y. So it's minus sin x, sorry, minus cos x sin y. These two are same, so I'll just keep cos x sin y. Then we have to differentiate this with respect to y, partial differentiate. So differentiation of sin y is cos y. We don't have any. So this is minus sin x cos y. Is this clear how we are doing second order differentiation for any other terms, like any other um, functions we have, like sine, trigonometric functions, or like that. Then del square f of pi by 2 comma 0. So when we substitute that, it's minus sine pi by 2 cos 0 minus cos pi by 2 sine 0 minus cos pi by 2 sine 0 minus sine pi by 2 cos 0. So the term will be, this is minus 1. Here cos pi by 2 or sine 0 will be 0. So this is 0. And then here again minus sine pi by 2 is 1. Cos 0 is 1. So it's minus 1. So this is our Hessian matrix. Okay. Based on the eigenvalues of this matrix, we can know whether we have a maxima or minima, like whether it's a convex or convex function. So the now we are trying to get first the quadratic approximation. So the quadratic approximation of f of x comma y equal to sin x cos y is f of, if you are confused, if you are confused, if you are using same f here and here, you can take g also. It's just approximation, quadratic approximation for this, right? So if you don't want to get confused, you can just replace the function name, because otherwise you'll get f, and if you are using f and f, you might get confused as well. So it's equal to f of x naught comma y naught is 1. So it's 1 plus, then we have x1, okay. Then we have x minus x naught. So that is how we will do x, y minus pi by 2, 0 we have. Okay. Then we have first order differentiation del of f pi by 2 comma 0 is 0 comma 0 plus, then we have to take second order differentiation pi by 2. Yeah, I mean, just for here, that's what I wrote, right? This will be equal to x minus pi by 2, y minus 0. Yeah, this will be equal to that. This is x1 and this is x naught. I just wrote it initial for initial step like that. So next, here it will be x minus x naught, y. So I am just writing it directly. Then we have Hessian matrix minus 1, 0, 0, minus 1. Then we have into x minus x naught transpose. So it's x minus pi by 2 and y. This is our function. So I will write it clearly, 1 plus x minus pi by 2 into y. First order differentiation is 0 comma 0 we got at x naught comma y naught plus 1 by 2 into x minus x naught into del square of f of x, Hessian matrix, into x minus x naught transport. These are just to make the matrix multiplication compatible and ready. So here, if we multiply these two, matrix multiplication, it will be equal to 0, 1 plus 0, plus 1 by 2 into, first I am multiplying first this two matrices, okay. So it is minus of x minus pi by 2. Sorry. Okay, just doing matrix multiplication. Then it is minus y into, sorry, okay, 1 plus, then 1 by 2. Now again we are having 1 by 2 and 2 cross 1 matrix. Okay, so we have to do matrix multiplication. For that, then we will have 1 by 1 matrix, that is minus of x minus pi by 2 whole square minus y square. Okay, so that is, you can leave this like this also. You don't have to expand, I feel, because x minus pi by 2 whole square plus y square. This is our given g of x comma y. Okay, this is our quadratic approximation for the function f of x comma y equal to sin x cos y. Okay, this is this part clear? So if you are asked questions like what is the constant term, so this is our expansion, expansion, right? This is how our expansion looks. So this will be our constant term. And what is the linear term here? Then you have to tell us this. And what is the quadratic term? Then you have to tell this part. Once you expand what you are seeing, that you can just answer. I think that part is clear if you see the options also when you are answering it. So is this clear? So one will be our linear part. We have, sorry, one will be our constant. 0 is our linear part. 0 comma 0 will be what we are having. And here we can have based on this values. Okay. Hessian, if they have asked for Hessian matrix, then this is our Hessian matrix. This part is our Hessian matrix. And then if they asked what is the quadratic part, quadratic term or linear term, if they use, then you have to give partial function. Okay, so is there any questions related to how to write quadratic approximation for um, trigonometric functions sin x cos y? Then we'll go with next problem. uh, f of x equal to 3x. One second. F of x comma y equal to 3x square minus 2xy plus 2y square plus 5x minus 7y. What is the eigenvalue for Hessian function? Hessian matrix of f of x comma y. So shall I wait for a minute? Can you guys tell me the eigenvalues for this function? Yeah, yeah, because Hessian matrix is the second order derivative, right? So can just take that directly and calculate the eigenvalues. We'll just wait for 1 minute. Now, then I'll also solve the problem. So I made this so that it will help you with your assignments, how they are giving questions. Based on that, I framed the questions. So I'll start doing the solution. You can tell me the answer, whatever you get, okay, in between also. So first they asked for eigenvalues of Hessian matrix, so we can directly calculate the Hessian matrix. So del square of f of x comma y is dou square f by dou x square, dou square f by dou x dou y, dou square f by dou x dou y, dou square f by dou y square. Okay, so that will be uh, okay. What I'll do is first I'll write dou f by dou x, that is 6x minus 2y plus 5. Dou f by dou y is minus 2x plus 4y minus 7. So del square f of x comma y is, again we have to differentiate the first term with respect, partial differentiate with respect to x, that is equal to 6. Then with respect to y minus 2. Then with this second term, second to get dou square f of dou y square. So this will be 4. Okay. So suppose in this case, we have our Hessian matrix 6x, 2y, 2y and 5y like this. So then what you will do? You just calculate 6x minus, how you will do the normal calculation to get eigenvalue. The determinant of this will be equal to 0. This is a minus lambda I form. The determinant of it will be equal to 0. Then we find lambda values. So these lambda values in this case will be in terms of x and y. Okay. So that means the lambda values are changing with respect to x and y. So suppose in the problem they gave us find the eigenvalues at x equal to 2 and y equal to 3, substitute x equal to 2 comma 3 at that point. Otherwise you have to report it like how you are getting it in terms of x and y. Okay, in our case they are not functions of x and y, so we get a constant eigenvalues for entire function. So this is our Hessian matrix, 6 minus 2 minus 1 4, and to get um, eigenvalues, it is 6 minus lambda minus 2 minus 2, 4. 4 minus lambda. Determinant of this will be equal to 0. So it's 6 minus lambda into 4 minus lambda minus 4 equal to 0. Okay. So 24 minus 10 lambda plus lambda square minus 4 equal to 0. So lambda square minus 10 lambda plus 20 equal to 0. So this we can solve like lambda equal to, this is in the form ax square plus bx plus c equal to 0 quadratic equation. The roots of that will be x equal to minus b plus or minus square root of b square minus 4ac by 2a. Okay. So it is 10 plus or minus square root of 10 square 100 minus 4 into ac, 4 into ac by 2a. A is 1 here. So 10 plus or minus root 20 by 2. So here root 20 can be 2 root 5, right? So on this I can write 5 plus or minus, because I'm dividing by 2, 5 plus or minus root 5. So based on the sign of this, so if you see lambda first is 5 plus root 5 and we have 5 minus root 5. Are these two positive or negative? Yeah, both are positive. So therefore we have a minima and the function is convex. Since you can see that it's convex function throughout the region because they are not varying with respect to x and y, right? So we have this minima as global minimum. You understood this? Next one is uh, next problem. Give a Taylor series approximation up to second order for value of f of 1.1 when we have f of 1.1 is equal to what? When we have f of 1 equal to 2, f dash of 1 equal to minus 3, f double dash of 1 equal to 4. Can you tell me what is f of 1 comma 1, 1.1 value? It's a single order, single variable function in f of x. Okay, they have given us f of 1, f dash of 1, f double dash of 1 value, and they are asking what is the Taylor series approximation value of f of 1.1. Just wait for 1 minute. Um, I'll just give you 1 minute. Think because I have given all the values, right? You won't be having a equation. I just want f of 1.1 value. How you are going to get it? It's not equal. You the approach is correct, but there is some yeah, approach is correct. But I need a value for f of 1.1, not in equation form. I need a final answer. Your approach is correct. Just think 1.1 represents what in that function? 1.1 is x naught or x1? Yeah. Yeah. Hmm. Hmm. Sorry, I didn't understand. What are you saying? I'll just write it here. What are you saying? F of it's not a second derivation. It's a second order approximation of for yeah, yeah. That's what we have to do here. But hmm, we have to use that f of x1 equal to this is small x1. Sorry, if is f of x naught plus f dash of x naught into x1 minus x naught plus f double dash of x naught by 2 into x1 minus x naught whole square. So in this, they have given, what did they give at x equal to 1? We have f of f value, f dash value and f double dash value. So that means these values are given. So x naught equal to 1 and x1 we have to find. F of 1.1 we have to find. So here x1 will be 1.1. So from this, f of 1.1 equal to f of 1 plus f dash of 1 into x1 is 1.1 minus x naught is 1 plus f double dash of 1 by 2 into x1 is 1.1, sorry, minus 1, x naught is whole square. So just substitute the values. F of 1 is 2, f dash of 1 is minus 3 into 1.1 minus 1 is 0.1 plus f double dash of 1 is 4 by 2 into 1.1 minus 1 is 0.1 whole square. So it is 2 minus 0.3 plus 0.02. So it's 1.72, f of 1.1. Okay. This problem is clear how we are doing this. You guys have the approach is correct. We have to use this, but you might get confused x1, x0, how to assume those values. So that's why I gave this problem. Okay, is this clear? Okay. So now what we will be doing is, until now we have seen optimization of single variable or multivariable without any constraint, how we are addressing it. Now if we have constraint, okay, constraint optimization, how we are going to solve it. We have minima or maxima function f of x. It can be single or multiple variable subject to gi of x equal to 0, and we have 1 to n constraint. Suppose how we are going to do. In that case, what we are having normally, we have, if we have a optimization problem f of x, we have these contours. Okay, at this particular point optimum will exist, minima or maximum. But now we have a constraint that it should satisfy g of x equal to 0. So it should be, I'm just assuming one line for now to give an idea. And this is a two-dimensional problem. Okay, x comma y. So in this case, what is happening? This particular, our minima or maxima is not lying on g of x. So it won't be satisfying the constraint. So that's not our answer. So if you see, in this way optimum is existing, we are seeing at this particular contour point, the value is close, it's either decreasing or increasing the function value. Okay, and it is also satisfying the constraint g of x equal to 0. So here in this case we have minima or maxima which satisfies constraint. Okay, so in that case, we have to do, sir has given Lagrangian multiplier approach, if you remember. So what we are having is, we have function minimization or maximization of f of x. And if we have g1 of x equal to 0, this can be capital X or small x. Okay. So first let me write for single variable for clear understanding. Then we have, suppose we have two constraints, g1 of x and g2 of x. Then we are having Lagrangian equation like L of x is f of x plus lambda 1 g1 of x plus lambda 2 g2 of x. Then we will solve the function. So how we will solve is, first we will take, since it's a single variable, so we are doing directly df of, sorry, since it's a single variable in x, okay, it's dl of x by d of x should be equal to 0, and we have other constraints dl of x by, no, still it will be partial derivative. Why? Because this L of x is in x comma lambda 1 comma lambda 2 are our variables. Okay, once we write this L of x function. So first dou L of x by dou x should be equal to this. This is our first constraint, and then dou L of x by dou lambda 1 should be equal to 0, and dou L of x by dou lambda 2 is equal to 0. So why we are taking these two? Initially only x is our variable, right? Why do we have lambda 1 and lambda 2? If we see dou L of x by dou lambda 1, so we will get g1 of x, because only lambda 1 is here, right? So that means this is g1 of x is equal to 0. That's our constraint. And then if we do dou L of x by dou lambda 2, we have g2 of x that's equal to 0. That is our second constraint. So for equality constraint, remember this is equality constraints, then we will directly add it to our main equation f of x with respect with using lambda 1 and lambda 2, or multiple lambdas if you have multiple constraints. Similarly, in the case if we have suppose function in multiple variables, f of x comma y, and we have constraints g1 of x comma y equal to 0, g2 of x comma y equal to 0. Then in this case, what are the conditions we will have? L of x comma y equal to, we have two constraints, so we have lambda 1 and lambda 2. This will be equal to f of x comma y less lambda 1 into g1 of x comma y less lambda 2 g2 of x comma y. And the conditions are dou L by dou x equal to 0, dou L by dou y equal to 0, then dou L by dou lambda 1 equal to 0, and dou L by dou lambda 2 equal to 0. See, we have four conditions and four variables, right? So using these conditions, we can get the values of lambda 1, lambda 2, and also x comma y where partial derivation will be equal to 0. So if you want to see the derivation and all, sir is explaining that. Okay. So that's why I'm not going through it. And suppose in our case, if we, here what I have given is g of x is equal to 0. And we are, sir has also mentioned if g of x equal to b. It's a constant. Then we are, he also explained if b value changes, increases or decreases, how the objective function f of x value is changing. Okay. So in that case, what was happening is the relation is d df is equal to lambda of dv. If you remember the derivation, or this is the relation between the change in the objective function and change in the constant. Okay. So if lambda is positive, okay, and we have a maximization type function, and suppose if the f of x value of maximum value is at is 24, then what will happen if we are increasing the value of b from b1 to b2? db is positive, right? And we know lambda is also positive. So then df will be also positive. So that means the f of at new optimum value, what will happen? It will be for 24 plus df. So with respect to change of the constant b in the constraint, the objective function value is also varying. Okay. Is this clear? Like, this is one case when lambda is positive and we have a maximization type and we are increasing the constant, then how the function value will be changing? It is also increased. Suppose we are from B1 to B0 we are doing, and we are reducing, restricting the constraint, constant value. This is negative and lambda is positive, then df will be positive into negative, it will be negative. So what will happen? The objective function will be decreasing because this is negative value. So it will be 24 minus some x, some value will be there. Okay. So the objective function will be decreasing in this case. Similarly, for minimization type also, sir has given, I'm giving small example. But if lambda equal to 0, then what is happening? df is equal to 0. So if there is any change in the constant, there is no effect on the objective function when the lambda is 0. Similarly, we will have two condition when lambda is negative. Okay. Is this concept clear? What is happening? Then let's solve few problems related to the this Lagrangian. Maximize f equal to 2x1 plus x2 plus 10 subject to x1 plus 2x2 square equal to 3. How does the Lagrangian looks like? That is L of x. How does it look? Can you tell me the equation? Lagrangian equation. Yeah. So if you remember, when we have maximization type f of x or minimization time, yeah, yeah, and we have a constraint g of x equal to b, then the Lagrangian will be in the form f of x plus lambda times b minus g of x. Okay, so that's why we have x1, x2 and lambda 1 because we have only one constraint, and x1, x2 are the variables already given. So the Lagrangian will look like 2x1 plus 2x2 plus 10 plus lambda 1 into b is 3 here. 3 minus x1 minus 2x2 square. This will be our Lagrangian. Okay. Is this clear? We should not be writing x1 minus 2, x1 plus 2x2 square minus 3. Okay. This is how you have to write b minus g of x. Then next problem, minimizing f of x comma y equal to 5x minus 3y, subject to constraint x square plus y square equal to 136. And what we have to do is what is the local minimum. You can tell me x comma y in terms of Lagrangian multiplier lambda. Okay. Where does the local minimum exist? We take for 1 minute. Any answers? Uh, no, I'm asking about x and y values. Where does the local minima exist? That's the Lagrangian, right? You told me x comma y comma lambda is equal to lambda 1, 5x minus 3y, okay, plus lambda 1, 136 minus x square minus y square. Right? This is what I want, the x comma y values where the local minima exists. 3 by 2 lambda, is the sign correct? Yeah, yeah, yeah. Yes, that's correct. So what we have to do, if you remember, the conditions are dou L by dou x equal to 0. So it's 5 minus 2x into lambda 1 equal to 0. So it's lambda 1 equal to 5, sorry, x equal to 5 by 2 lambda 1. Okay, lambda or lambda 1, anything is fine. So dou L by, next condition is dou L by dou y is equal to 0. So it's minus 3, okay, minus 2 lambda 1 into y is equal to 0. So y is equal to minus 3 by 2 lambda 1. Okay, and other condition is dou L by dou lambda 1 equal to 0. But I'm just asked, we already got these two, that what will be the x comma y where the local minima exist in terms of lambda. Okay. So from this case, if you want to see if dou L by dou lambda 1 equal to 0, it's 136 minus x square minus y square equal to 0, right? So to get, if you want exact values of lambda, x and y, then what we can do is 136 minus x is 5 by 2 lambda 1 whole square minus y is minus 3 by 2 lambda 1 whole square equal to 0. So when you solve this, we get lambda values. Okay, I think maximum 2 you will get because we will have a second order equation here. Then substitute these values in this 2. Okay, in this 2, x comma y, and then you will get x comma y value also. Okay, that's how we will solve a Lagrangian problem with optimization problem for optimization problem with equality constraints. So next, yeah, 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 we have to always with b minus g, right? If it is minimum, I told in minima or maximum, anything we have to write. I mean, when I'm saying, yeah, b minus g is what you will be writing here when you have g of x equal to constant b minus g. It doesn't depend on the type of optimization, minima or maxima type of optimization. We have to write g minus b. Hmm. No, 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 we don't have to because we are just doing a first derivative, right? We are just trying to find where it is equal to 0. That condition is satisfied by both minima or maxima, if you remember. Yeah, that's why he didn't mention, sir didn't mention anywhere like whether, I mean, where we have to convert from, if you see, minima. Yeah, only in simplex method we are converting to minimization type because we have standard optimization form, right? The objective function will should be minima and constraint should be equality signs. Yeah, so that's where we are converting. Here we don't have to. So then we have minimization function f of x1 comma x2 comma x3 equal to x1 square plus x2 square plus x3 square. Find the minima with constraints x1 plus x2 plus x3 minus 6 equal to 0. See here, the constant is already on this side. Okay, so just it is, this entire thing will be g of x. I'm giving on the right hand side the value as 0, so it will be g1 of x equal to 0 directly. Okay, you don't have to do b minus g here. Don't get confused. When I have g1 of x equal to 0, we need to have in this format. But if the equation is given x1 plus x2 plus x3 equal to 6, then we will write 6 minus x1 minus x2 minus x3 equal to 0. This is our g1 of x in this case. Okay. But here what is given x1 plus x2 plus x3 minus 6 equal to 0. So this is directly g1 of x equal to 0. Is this clear? Yeah, when we have constant given separately, then you have to apply that condition. Okay. So this is one of the constraint. x1 plus x2 plus x3 minus 6 equal to 0 and x1 minus x2 plus 2x3 minus 3 equal to 0. So can you guys tell me where minima exists, that is x1 comma x2 comma x3 star values, where minima exist and minimum value of capital F, sorry, f of x. See here I'm writing capital X to represent x1, x2, x3 all together in this case. So I just wait for 1 minute. I know this will take a little bit time, but I'll just give 1 minute and I'll start the solution. Sorry? Yeah, you guys can solve. I will also solve parallelly, I mean after 1 minute, so that then you can see if there is any mistake I'm doing or you guys are doing, then we can just discuss. Okay. So just start solving it. You can tell me the answer whenever you're done. Okay. So the Lagrangian L of capital X, which represents x1, x2, x3, all the three variables, is equal to f of x plus we have two constraints. So lambda 1 g1 of x plus lambda 2 g2 of x. And remember we have in Lagrangian capital X lambda 1 comma lambda 2. Or you can give that lambda 1 and lambda 2 also, lambda is the variables. So L of, so x comma lambda, or I think this might confuse little bit, x1 comma x2 comma x3 comma lambda 1 comma lambda 2. So these are all the variables involved, will be x1 square plus x2 square plus x3 square plus lambda 1 times of x1 plus x2 plus x3 minus 6. This is the first constraint, plus lambda 2 of x1 minus x2 plus 2x3 minus 3. Okay. So this is our Lagrangian. So what are the conditions we will have then? Dou L by dou x1 equal to 0. So that's 2x1 plus lambda 1 plus lambda 2 equal to 0. So it's x1 is equal to minus of lambda 1 plus lambda 2 by 2. Okay. Then dou L by dou x2 equal to 0. 2x2 plus lambda x1, 2x1 plus lambda 1 plus lambda 2 equal to 0. So x1 is minus of lambda 1 plus lambda 2. No, actually, this means minus lambda 1 minus lambda 2 by 2. Yeah, minus is outside the bracket. Yeah, I'm just taking minus out. So this minus is, yeah, yeah. Just I'm taking minus 1 outside and writing like this. Minus 1 times of lambda 1 into, I mean, lambda 1 plus lambda 2 by 2. So partial differentiation with respect to x2, 2x2 plus lambda 1 minus lambda 2 equal to 0. So x2 will be lambda 2 minus lambda 1 by 2. Do now next is the partial differentiation with respect to x3. So it is 2x3 plus lambda 1 plus 2 lambda 2 is equal to 0. So x3 equal to minus lambda 1 minus 2 lambda 2 by 2. Okay. Then we have other conditions, dou L by dou lambda 1 equal to 0. So that's will be, so our first condition x1 plus x2 plus x3 minus 6 equal to 0. Dou L by dou lambda 2 equal to 0. That will give us our second constraint x1 minus x2 plus 2x3 minus 3 equal to 0. Okay. So now what I will be doing is, this are in terms of x1, x2, x3. So I'll just substitute these equations which we have x1 and x2, x3 values in terms of lambda 1 and lambda 2 in these two equations. So that minus lambda 1 minus lambda 2 by 2. Okay. I'm substituting in this first equation plus lambda 2 minus lambda 1 by 2 plus minus lambda 1 minus 2 lambda 2 by 2 minus 6 equal to 0. So directly what we can do, minus 1 minus lambda 1 minus lambda 2 plus lambda 1 minus lambda 1 minus lambda 2 minus 2 lambda 2 minus 12 equal to 0. Sorry. I think when I'm saying it, I'm making the mistake. Okay. So this is what we will get. So these two will get cancelled. So it will be minus 3 lambda 1 minus 2 lambda 2 minus 12 equal to 0. So that's to 3 lambda 1 plus 2 lambda 2 plus 12 equal to 0. This is our one of the main equations we get in only lambda and lambda. Now this also, in this also we'll substitute x1, x2, x3 values in terms of lambda 1, lambda 2, lambda 3. So that will be minus lambda 1 minus lambda 2 by 2 minus of lambda 2 minus lambda 1 by 2 plus 2 times of minus lambda 1 minus 2 lambda 2 by 2 minus 3 equal to 0. So since we have divided by 2, I'm doing just however I'm feeling easy. Okay. Minus lambda 1 minus lambda 2 minus lambda 2 plus lambda 1. Okay. Minus 2 lambda 1 minus 4 lambda 2 minus 6 equal to 0. I'm just moving this to here, the divided by 2 term. Now, lambda 1 will get cancelled. Minus 2 lambda 1 minus 6 lambda 2 minus 6 equal to 0. If I take 2 minus 2 out, lambda 1 plus 3 lambda 2 plus 3 equal to 0. This is the second equation we have. So using this and this, we can solve lambda values, right? So 3 lambda 1 plus 2 lambda 2 plus 12 equal to 0. And I'm multiplying second equation with 3. 3 lambda 1 plus 9 lambda 2 plus 9 equal to 0. We subtract minus 7 lambda 2 minus 3. Sorry, plus 3 equal to 0. So lambda 2 yeah, is 3 by 7. Now to get lambda 1, I'm just substituting it in lambda 2 value in equation 2 plus 9 by 7 plus 3. 3, 7, 21, 30 by 7. So lambda 1 is minus 30 by 7. Okay, we have lambda 1 and lambda 2 values. So now x1 is, if you remember, we have minus lambda 1 minus lambda 2 by 2, right? So it's minus 3 by 7 plus 30 by 7 by 2, 27 by 14. That's what we'll get. Next, x2 is lambda 2 minus lambda 1 by 2 minus 30 by 7 minus 3 by 7 by 2, that is minus 33 by 14. Next, x3 is minus lambda 1 minus 2 lambda 2 by 2, that is minus 3 by 7 plus, since lambda, okay, 1 second. Lambda 1 is minus 30 by 7, right? 30 by 7 minus 6 by 7 by 2. 24 by 14. That is divide to 12 by 7. Okay. So at this point, x1 comma x2 comma x3 equal to 27 by 14 minus 33 by 14 and 12 by 7. We have a optimum value. They have already given minimization problem, and the minimum value is, we have to substitute this in the function. Okay, x1 square plus x2 square plus x3 square. So that's approximately, you will get like 12.21. Okay. So is this clear how we are applying Lagrangian method for optimization when we have equality constraints? Okay. So also, while I'm solving, I got this problem that we are discussing, right? How we will know whether the function is convex or concave. So when we have, I'll just discuss this one problem and then we'll end the session for today. If you have any questions, you can ask me whether this is convex or concave. Was the question. Remember. If you understand till the quadratic approximation method, and that is for um, solving minimization or maximization type of objective function without any constraints. And next, we discussed about Lagrangian multiplier method, where we will be solving optimization problem with equality constraints. Okay, so these two topics we have covered. If you don't have any question in that, then I'll explain this problem also how we will be doing. Then we will end the session. Okay. Okay. So, like I said, we will be developing Hessian matrix first for this. So, what is Hessian matrix? It is a double differentiation, right? So, the double differentiation, when we have two variables, it's a 2 by 2 matrix. When we have three variables, it's a 3 by 3 matrix. So, that is dou square f by dou x1 square, dou square f by dou x1. Next, we will again differentiate with respect to x2. The third term will be dou square f by dou x1 dou x3. Next is in second row we have first derivation. We have two derivations, right, in dou square. So first will be always with respect to x2 in this second row, and then x1 dou square f by dou x2 square. This first and second will be both by x2. Next, dou square f by dou x2 dou x3. Okay. The last row will the first differentiation with respect to x3, then x1, x3, x2, dou square f by dou x3 square. Okay, basically this is x1, x2, x3. Here okay, don't get confused like this. Is this clear how I wrote the 3 by 3 matrix? No, okay. So if you, okay, first let me write if it's in terms of x1 comma x2. How are you writing dou square function? Dou square f by dou x1 square, dou square f by dou x1 dou x2. Then actually what we should be writing is dou square f by dou x2 x1, then it will be dou square f by dou x2 square. This is how the 2 by 2 matrix looks like, Hessian matrix. This one you know, right? How we'll be doing? Okay. So in this case, what we will do is the first term. Here we are initially also deriving, partially deriving with x1 and then x1. That's why we have dou square f by dou x1 square. Okay. The second term, let us use different color. Second term, if you see, first partial differentiation with respect to x1, then we will differentiate with respect to x2. And this term, first we will differentiate with respect to x2 and then with respect to x1. This one is x2 and x2. If you remember, this looks like the position, you see, 1 comma 1, 1 comma 2, 2 comma 1, 2 comma 2. That's how we represent the position, cell position in the matrix, right? Is that clear? This you know, Hessian matrix for 2 by 2 matrix, 2 by, I mean, 2 variables, right? How we are writing. This is what I'm just explaining you how we wrote that. If you have any questions, I can explain this. Then I'll go with how we are writing 3 by 3 Hessian matrix. This 2 by 2 is clear, right? Okay. Then if we are going for 3 by 3, see, remember the positions. Okay. First, let's write the position of each cell. It's 1 comma 1. First row, second column. First row, third column. Second row, first column. Second row, second column. Second row, third column. Third row, first column. third row, second column, third row, third column. Okay, this part you understood. So here just replace 1 comma 1 by x1 like that. If you have 2, it will be x2. 3, it will be x3. Okay. So dou square f by dou, it is 1 comma 1 cell, right? Dou x1, dou x2 will be dou x1 square. Next we have 1 comma 2. So dou x1, x2. Okay. 1 comma 2. Then it is dou square f by dou x1, x3. Next it is dou square f by dou x2, x1. Generally these two will be same, like we get in our 2 by 2 matrix also. It will be a symmetric matrix, okay, whenever you have this kind. Next it will be dou square f by dou x2 square. Then it will be dou square f by dou x2, x3. Then if you see, it's a 3 comma 1. So dou square f by dou x3, x1. Then 2 comma 2. Sorry, 3 comma 2. Dou square f by, yes, x3, x2. Dou square f by dou x3 square. This is how, yeah, this is how we write 3 by 3 Hessian matrix. Like that, you can write n by n also if you have more than that. But the computation will be difficult, right? So mostly they won't be giving you higher order functions more than that. So if you see, it will be a symmetric matrix. This will be equal to this. This will be equal to this. And this will be equal to this. Okay. So now, do you want me to solve this now, or you want me to end the session because it's already past 9? So just like how we did for yeah. So what sorry? Okay, so our function is x1 square minus x2 square minus x3 square plus x1 x2 plus x1 x3 plus 2x1 minus 5x3 plus 2. Okay, first derivation I am doing with respect to x1, 2x1 plus x2 plus x3 plus 2. Okay, then partial differentiation with respect to x2 minus 2x2 plus x1. Yeah. Hmm. Yeah, that's what I have told you, right? Initially also, if we have it in terms of x1, x2, x3, either they will give find the eigenvalues at x1 equal to 2, x2 equal to 3 or something like that. They'll give the yeah, or else you have to find eigenvalues in terms of x1, x2, x3 only. Yeah, there, that's what I told, right? When the x1, x2, x3 values are changing, these eigenvalues also is changing. Suppose if you got like lambda equal to x1 square. Suppose this is the eigenvalue you got. Then you know whenever the whatever the values of x1, it's always positive. So in that case, you can confidently say whether it's a convex or concave. But if you have eigenvalues as x1 minus x2. This can be negative or positive. So based on the range x1, x2, x3 ranges that they have given, then we will know whether it's a concave or convex. But I don't think because sir didn't touch that deep into this problem. So I don't think they will ask you, but like this, mostly it will be in constants only if you are going for like high number of variables. The Hessian matrix will be constant only. I mean, you can get eigenvalues, constant values. Okay. So then coming to this, dou f by dou x2 will be, yeah, this one. Then dou f by dou x3 is minus 2x3 plus x1 minus 5. Then now we are writing Hessian matrix. First one is dou square f by. So first this one we have to divide partial differentiate with respect to x1, x2, x3 to get first row. Okay, so it is 2, 1 and 1. Then this for second row we have to partial differentiate with respect to x1, x2 and x3. So it is 1 minus 2, 0. So for third row, this we will partial differentiate in the order of x1, x2, x3. So it is 1, 0, minus 2. So this is the Hessian matrix we got. Now 2 minus lambda 1, 1, 1 minus 2 minus lambda 0, 1, 0 minus 2 minus lambda. This determinant is equal to 0. Then you know, right, you have to take 2 minus lambda common and then you have minus 2 minus lambda 0, 0. How you will do for, how do you find differentiation, sorry, determinant for 3 by 3 matrix. So like that you have to continue and get the values of lambda. This is little bit long, but I think you guys, I hope you understood this procedure. If they ask in case, how we will know whether it's a convex or concave. If they give like multiple variables more than two also, they'll be giving you simple problem so that you can get the eigenvalues. Okay. Any questions? Okay. Assignment question, right? Assignment question 2. You are talking about, okay, week 4. Okay, I'll check. This, okay. Yeah. Okay. Okay. Okay, guys. Thank you so much for attending. Yeah. Thank you.